Swayam Prabha. Digital India. Educated India.
Hello everyone. Today we are going to discuss order or exponent of polynomials over finite fields. So, let us consider a polynomial f over finite field fq, which has degree m, which is greater than equal to 1, and suppose it has a constant term, non-zero constant term. That means f of 0 is not equal to 0. For such a polynomial, there exists an e such that e, a natural number, such that f of f x divides x power e minus 1 and e is less than equal to q power m minus 1. So, let us see the proof. The proof is quite simple. We consider powers of x, x power 0 equal to 1, x power 1, x power 2, etc., but every time we take modulo f x. Now, modulo f x, how many polynomials are there? Which are basically all polynomials of degree less than m, and there are q power m such polynomials. And since all these powers are going to give non-zero polynomials, because this f x does not have x as a factor. So, these are all going to give non-zero polynomials. So, there are q power m minus 1 such polynomials. So, if I take consecutive q power m powers, that is x power 0 to x power q power m minus 1 modulo f x, then there must be a repetition. That means x power I must be equal to x power j modulo f x for some I not equal to j. In fact, for some, we can say for some I less than j, which means that f x divides x power j minus x power I, which is x power I times x power j minus I minus 1. But since f x does not have x as a factor, this means f x divides x power j minus I minus 1. So, that says that there is such an exponent e. In this case, e is j minus I. So, for a polynomial f x which does not have x as a factor, there is always such an exponent e for which f x divides x power e minus 1. Now, the exponent or order of a polynomial is the smallest such exponent, smallest such e for which f x divides x power e minus 1. Definition: if we take f x such that f of 0 is not equal to 0, then the order of f, it is called the order of f, exponent of f, and also sometimes the period of f. Order of f is the smallest e such that f x divides x power e minus 1. Now, on the other hand, if f x is of the form x power t times g x, where g of 0 is not equal to 0, that is if x is indeed a factor of f x, then there cannot be such an e for which f x divides x power e minus 1, because x power e minus 1 does not have a factor x. So, x cannot divide it. So, in that case order of f is defined to be order of g itself, that is take all the x factors outside and then what remains which does not have any factor x, the order of that polynomial is defined as the order of f itself. Now, we would like to get some understanding of what is the order of any given polynomial. Now, we know that any polynomial can be factorized into irreducible factors. So, in general any polynomial can be factored uniquely as a constant times f1 x power b1, f2 x power b2 up to fk x power bk, where these polynomials are irreducible, distinct irreducible polynomials. Distinct irreducible polynomials. So, any polynomial can be uniquely factorized in this way. So, first we would like to understand how to find or what kind of order irreducible polynomials have, like f1 x, f2 x, and then we will try to understand what kind of order their powers have, f1 x power b1, f2 x power b2, each of them what is their order, and then we will try to see how to combine and get the order of the product of such co-prime factors. So, towards that, the first result that we will discuss is about irreducible polynomials. If f is a polynomial over f q, degree is m and f is irreducible, and we will first consider that okay, so f is irreducible, then f can be a constant times x. It cannot be constant times x square or x cube, because then it is not irreducible, but it can be a constant times x. But we will not consider this type of polynomial, we will first consider polynomials for which x is not a factor. So, if so for Cx type of polynomial, we know that its order is defined as the order of C itself, that is 1, because x is taken out. So, the order of constant 1 is just 1 itself. So, now if you have an irreducible polynomial, order of f is same as the order of any of its roots. So, f will have its roots in some extension field, and in that extension field there is the multiplicative group. In that multiplicative group the elements have order well defined, number of times you multiply, so that you get 1. So, first of all let us take, suppose alpha is a root in some extension field, alpha is a root of f, that is f of alpha is 0, then we know that order of all the roots of f are the same. So, it does not matter which root we take, and since f is irreducible, we know that f is the minimal polynomial of alpha, is the f is the minimal polynomial of alpha. So, now we can say that if E is such a number for which alpha power E is 1, suppose E is an integer for which alpha power E is 1, then this is true if and only if alpha is a root of x power E minus 1. This is from the definition. It means that if you put alpha in place of x, alpha power E minus 1 is 0 because alpha power E equal to 1, and these are equivalent statements. Now, because f is the minimal polynomial of alpha, this is true if and only if f x divides x power E minus 1. Alpha is a root of any polynomial if and only if that polynomial is a multiple of its minimal polynomial, which is f x. So, now the order of alpha is defined as the smallest e for which this holds. Order of alpha is the smallest e for which the first statement holds. Order of f x is the smallest e for which this statement holds, right, and these two statements are equivalent, which means the order of alpha is same as order of f. Right. So, this proves the statement. Okay. Now, we will consider a corollary of this lemma, which says that if f x is irreducible, again degree is m, then order of f divides q power m minus 1. Why is that? Let us consider two cases. Now, we are not saying f of 0 is not equal to 0. So, if f of 0 is 0, it is irreducible. So, it means it can be only of the form c times x, in which case the order is 1, which means it divides q power m anyway, right. Order of f divides q power m minus 1. Now, if it is not of this form c x, then f of 0 is not equal to 0. Then we can use this lemma we just mentioned, and we know that order of f is same as the order of its roots, and order of its roots are there in the field extension field f q power m. That means those roots have orders which divide q power m minus 1. They are elements of the multiplicative group of f q power m, and hence their orders divide q power m minus 1, and hence order of f itself divides q power m minus 1. That proves the corollary. Now, let us take some examples to see to get a feel for the order of irreducible polynomials. Let us take degree m equal to 4 and q equal to 2. So, we will consider polynomials of degree 4 which are irreducible, and we have already seen these examples before. X power 4 plus x plus 1 is an irreducible polynomial, x power 4 plus x cube plus 1 is an irreducible polynomial of degree 4, and also x power 4 plus x cube plus x square plus x plus 1 is an irreducible polynomial. There are these three irreducible polynomials of degree 4. Now, the order of this is 15, and of course, all these polynomials divide the polynomial x power 15 minus 1. So, the order of them divide 15, but in this case these two have order exactly 15. So, 15 is the smallest number for which x power 4 plus x plus 1 divides x power 15 minus 1, and 15 is the smallest number for which this also divides x power 15 minus 1, but the order of this is 5. This is irreducible of degree 4, but it has a smaller order 5, because x power 4 plus x cube plus x square plus x plus 1 also divides x power 5 minus 1. So, 5 is the smallest number for which this happens. So, the order is 5. So, these are the orders of these polynomials. Now, if we can also see what their roots are. So, their roots all belong to f 2 power 4, that is f 16, and one can construct f 16 as the residue ring f q x modulo one of these polynomials. Let us take x 4 plus x plus 1. One can take all the polynomials modulo x 4 plus x plus 1, that forms a field, and if you construct it this way, the polynomial x is a root of x 4 plus x plus 1, right. So, the other roots of x 4 plus x plus 1, the roots are alpha, alpha square, alpha power 4 and alpha power 8. These are the conjugates of alpha, and this whole set, they are the roots of this polynomial. Now, if we take x power 4 plus x cube plus 1, we will see that its roots are x power alpha power 7, alpha power 14, alpha power 13 and alpha power 11. And you can see that all of these are primitive elements of f 16. Alpha is a primitive element, then these are all relatively prime to 15. These powers are all relatively prime to 15, and hence these other powers that we have written are also primitive elements. Now, however, x power 4 plus x cube plus x square plus x plus 1, its roots are not primitive elements. Its roots are alpha cube, alpha 6, alpha 9 and alpha 12. These are not relatively, these powers are not relatively prime or coprime to 15. And what is the order of alpha 3? It is not 15, because these are not primitive elements. Its order is 5. Order of any of these alpha power 3, for example, is 5, which is same as the order of this. Is also 5. So, it is the same as the order of its roots. Okay. Next, we will see a few very simple lemmas. If you take any positive integer and a polynomial f which has a non-zero constant term, then f x divides x power c minus 1 if and only if order of f divides c. So, how do we prove this? Let us prove the opposite direction first. That is, first we assume that this c is a multiple of the order of f, that is c is m times e, let us say, where this order of f is denoted by e. Then we will show that f x divides x power c minus 1. But we know that if this holds, then x power e minus 1 divides x power m e minus 1, and f x divides x power e minus 1. So, these two together implies that f x divides x power m e minus 1. F x divides x power e minus 1 and that divides x power m e minus 1. So, that is simple. Now, the other direction, suppose f x divides x power c minus 1 and then we want to prove that C is a multiple of E. So, let us divide C by E and we get a quotient m times E plus a remainder, where the remainder is between 0 and it is less than E. Then x power C minus 1 can be written as x power m E plus r minus 1, which we can write as x power m E minus x power m E minus 1 times x power r plus x power r minus 1. So, now if you look at this, this is divisible by f x, it is given, and this is divisible by f x because it is divisible by x power e minus 1, which is divisible by f x. So, this also must be divisible by f x. But then r is smaller than e, r is smaller than e. So, it is a smaller constant, an integer for which f x divides x power minus 1. The only r for which that can happen is r equal to 0, because e is the exponent and r is smaller than e. So, that means E divides C. That proves the lemma. Now, a corollary of this is that x power, if you take any two integers x power e and c, then x power e minus 1 divides x power c minus 1 if and only if e divides c. You can take x power e minus 1 in place of f x itself, its exponent then is e itself. Exponent of a polynomial of the form x power e minus 1 is e. So, by applying this result for such a polynomial, we get that x power e minus 1 divides x power c minus 1 if and only if e divides c. Now, a further corollary of this is that if you take two polynomials of the form x power e1 minus 1 and x power e2 minus 1, then their GCD is nothing but x power GCD of e1 e2 minus 1. You can argue this yourself, this is a very simple consequence. Now, let us look at a more general form of polynomial. So far we have considered only irreducible polynomials. Now, let us look at a more general polynomial, which are powers of irreducible polynomials. So, if you take a polynomial f x, which is g power b, where g is irreducible, and g of 0 is not equal to 0, then what is its order? What is the order of f? So, the order of f is computed in the following way. We take the smallest, suppose t is the smallest integer such that b is less than p power t. And what is p? P is the characteristic of f q. P is the characteristic of f q. That is the prime number of which q is a power. Then we take the smallest power of p, which is greater than b. Then the order of f is the order of g times p power t. Why is this? We will skip the proof of detailed proof of this. You can look it up in the book by Little and Narrator, but the idea is the following. If g divides x power e minus 1, then g power b will divide x power e minus 1 power p power t. Why is that? Because now p power t, because p power t is greater than equal to b, and this is equal to x power e times p power t minus 1. Why? Because we are doing all these operations over f q, and p is the characteristic of that field. So, if you power any polynomial by p or powers of p, that powering distributes over all the terms, and 1 power p power t is same as 1. So, this term remains unchanged and this power comes to only this term. So, g power b divides this, and hence clearly this is greater than equal to the exponent of this polynomial, but one can argue that this is the smallest such number, and hence that is the exponent of g power b. Okay, so now we know how to express the exponent of a power of an irreducible polynomial. For an irreducible polynomial, the exponent is a factor of q power m minus 1, and if you take power of an irreducible polynomial, this is how the order changes. Now, what if we have a product of such factors, product of such powers of irreducible polynomials? So, before going there, let us look at some examples to see how the exponent changes. Let us look at f x equal to a polynomial of the form c times x power b. What is the order of a polynomial of this form? First of all, the order of x is defined as 1. So, order of this is just p power t, where p power t is such that p power t is greater than b, greater than equal to b. So, similarly, if you take f x equal to x power 4 minus plus x plus 1 power 3, its order is 15 times, what is the power of 2, smallest power of 2 which is bigger than 3? It is 2 square, that is 4, 2 square. So, this is 60. Similarly, if you take f x equal to x power 4 plus x cube plus x square plus x plus 1, its order is 5, but if you take power 5 as well, then its order will be 5 times, what is the smallest power of 2 which is bigger than 5? Is the third power, 2 power 3, which is 8. So, 5 times 2 power 3, that is 40. This is the order of this polynomial. Now, if you take product of such powers of irreducible polynomials, how does the order change? Let us look at that. So, if you have irreducible polynomials g1, g2 up to gk, these are irreducible, and f is g1, sorry, these need not be irreducible. Let us just consider co-prime. They themselves may be powers of irreducible polynomials, for example. So, and if we take product of such polynomials g1, g2 up to gk, then how is the order of f related to the orders of g1, g2 up to gk? That is what we want to know. And the answer is order of f is the LCM of order of g1, order of g2, order of gk. Let us prove this. Again, the proof is quite elementary. Suppose I call the order of ei, ei is the order of gi, and I call the order of f as e. Then we know that gi divides x power ei minus 1, but because e is divisible by ei, this implies that gi divides x power e minus 1, which also means that, now this is true for all I. That means that f also divides x power e minus 1, because if every gi divides x power e minus 1, the LCM of gi's, which is f, the product of gi's are co-prime, so their product is same as their LCM, so that will divide x power e minus 1 as well. So, f divides x power e minus 1, but that may not mean that e is indeed this e. Okay, what is this e? Actually, we define e to be the LCM. We will show that this is the order. Right. So, because EI clearly divides the LCM, E, GI divides x power e minus 1. So, now f divides x power e minus 1, and hence E must be a multiple of the order of f, but now we will show that E is indeed the order of f. So, let us take any S, consider any S such that f divides x power s minus 1. We will show that E is less than equal to s for such an S. So, E would be the smallest E exponent for which this f divides x power e minus 1, and indeed we will in fact show that E will divide any such S. So, let us see that f divides x power s minus 1 implies that GI divides x power s minus 1 for all I, because f is the product of GIs, which means that x power ei minus 1 divides x power s minus 1. Why? Because ei is the order of GI. We have seen that GI divides x power s minus 1 if and only if this ei, which is the order of GI, divides s, and that is if and only if x power ei minus 1 dividing x power s minus 1, and that is so same as in fact ei dividing s. So, now this holds for all I, which implies that their LCM, which is E, must divide S. So, E is the smallest number for which this happens, and hence the order of f is E, which is the LCM of the orders. So, the final theorem says that if we have a polynomial of the form A times an irreducible polynomial powered b1, another irreducible polynomial powered b2, and so on up to fk bk, then these are each monic irreducible polynomial and let t be the smallest integer such that which is greater than equal to all the powers b1, b2 up to bk. T is the smallest integer such that p power t is bigger than equal to b1, b2 up to bk, each of them. Then the order of f, then the order of f is p power t times the LCM of order of f1, order of f2 up to order of fk. So, this is simply, it is also same as one can, it is easy to understand why this is true, if we look at this as LCM of p power t times order of f1 p power t times order of f2, p power t times order of fk. P power t can be taken outside the LCM, that is a common factor. So, again we will not prove this, this is quite simple to prove, we will leave it as an exercise. Now, there is another result which is worth mentioning here, another two results, we will again mention them without proofs, that we have seen that for irreducible polynomials the order divides q power m minus 1, where m is the degree of the polynomial. When is that exactly equal? The order is equal to q power m minus 1, when does that happen? And it turns out that that happens exactly when the polynomial is a primitive polynomial. So, f is irreducible, f of 0 is not equal to 0, then order of f equal to q power m minus 1 if and only if f is primitive. And because of this result, primitive polynomials are of importance in such context. Wherever we want large order, polynomials with large order, we want a primitive polynomial like that. So, another relation that is of importance is in the context of reciprocal polynomials. What is a reciprocal polynomial? If we have a polynomial f x which is a naught plus a 1 x plus up to a n x power n, its reciprocal polynomial is defined as f star of x, which is equal to x power n times f of 1 by x, but it is easier to see as it is same as a naught x power n plus a 1 x power n minus 1 plus a naught. That is, we reverse the coefficients, we take a naught as the coefficient of x power n, this goes here, this comes here, we reverse the order of the coefficients, that is defined as the reciprocal polynomial. And an interesting result is that order of reciprocal polynomials is the same, order of f is same as order of f star. Again we will not prove this. Okay. This concludes our discussion on order of polynomials.